Hi everyone, my name is Ridham. Today I'll be presenting on Bayer interpolation, specifically the bilinear demosaicing algorithm. I'll explain how single sensor cameras capture color, why they only get one color per pixel, and then walk through the bilinear algorithm that reconstructs the full color image from that incomplete data. Let's start with the problem. Most cameras, your phone, webcams, basically everything use a single sensor with the Bayer filter on top. The standard pattern is RGGB, group of 4 pixels with one red, two green, and one blue. You can see the pattern on the right, RG alternating on even rows and GB alternating on odd rows. Why two greens? Human eyes are more sensitive to green. Having two green samples per group gives us lower noise and higher perceived image quality. The consequence is striking. At any given pixel, we only measure one of the three color channels. That means two-thirds of our image data is not directly measured. We have to estimate it. That estimation process is called Bayer interpolation or demosaicing. So how do we fill in those missing colors? The idea behind bilinear interpolation is simple. For each pixel, we already know one channel, the one our filter measured. To estimate the other two, we look at the nearest neighboring pixels that have those colors and we average them. Because the Bayer pattern has four different pixel types, we have four cases. At a red pixel, we know red and estimate green from four cross neighbors and blue from four diagonal neighbors. At a green pixel on a red row, red comes from two horizontal neighbors and blue comes from two vertical. Case 3 mirror is the mirror of that one, and at a blue pixel, it's a mirror of case 1. So this is the most important visual. Let me walk through each case in detail. So this case 1, we are at a red pixel. That's the center with the black square. For the green, the four green cross neighbors contribute. You can see the green circles and arrows pointing inward from above, below, left, and right. For blue, the four diagonal blue neighbors contribute. These, those are the blue circles at the corners. Now for case 2, now we are at a green pixel on a red row. Red comes from just two horizontal neighbors, left and right, and blue comes from the two vertical neighbors. Notice that the fewer neighbors means less averaging, which can mean slightly more noise in the estimate. And similarly for case 3 and case 4. Case 3 would be the mirror of case 2 and case 4 would be the mirror of case 1. Another way to think about bilinear interpolation is as convolution. Each of the four cases maps to a 3 by 3 convolution kernel applied to the appropriate color channel. The cross kernel uses quarter weights in a plus pattern. This estimates green at red or blue pixels. The two neighbor kernel uses half weights either horizontally or vertically. This estimates red or blue at a green pixel. And the diagonal kernel uses quarter weights at the corners. This estimates red at blue pixels or blue at red pixels. One particular detail is that we can't interpolate the outermost row and column of pixels because the kernel needs neighbors on all sides. So we skip one pixel border. Now, let me walk through a concrete example of how it's calculated. So here's a small section of Bayer grid. We are at position 2 by 2. You can see the values on the grid are 145, 152 below, 148 to the left. So by averaging these four values on the green one, we get value roughly about 149. And for the blue diagonal one, we add them up and average them and we get the value 81. So this is how we get all the three values for the color channels. So now let's see what this looks like in practice. Here's a synthetic test image going through the full pipeline. The top left is the ground truth, top right is the raw sensor output, and one value per pixel, which is why it looks grayscale. Bottom left is the result of our bilinear interpolation, And this one is the error map, and the brighter means there are more errors. You can clearly see that the errors concentrated at two places. The sharp color boundaries between regions, and in the high frequency stripe region at the top. Smooth colored areas reconstruct almost perfectly, and this makes sense because bilinear interpolation is averaging, which works great when color changes gradually but fails when they change abruptly. Now let me show you on a real image. I coded this up. So this is a demo of bilinear interpolation, and here's my C++ implementation. Here I've implemented all the four cases that I showed earlier. So as you can see, red is the cell that we are measuring, and we are averaging the values for green and the blue, and similarly we are doing for others. Now I'll just show you a demo on an image. So here you can see this was the original image, and this was the original image. You can see like this is the nearest neighbor with the most noise. You can see how the image is changing. Now, so here's the zoomed comparison that we saw earlier. So this top left is the original. You can see the clean house siding lines. And this one is the nearest neighbor. The sliding turns into basically rainbow stripes, like some where different colors are coming. And the quality is clearly terrible with the red lifesaver you can see. And this one is our bilinear result, which is much better than nearest neighbor, but you can still see some different colors coming in the fence. And this one is the edge aware. This is the OpenCV implementation. And this is clearly the cleanest of the three with, you can see how the fence differs in all of these. And this is the error maps that make the artifacts even clearer. Look at the NN error. Those bright red and blue horizontal stripes are everywhere, especially on the house siding. That's the zipper effect. At sharp edges, averaging pulls values from wrong sides, creating alternated color fringes. Bilinear error is much darker overall. Errors concentrate along edges rather than being everywhere, and edge aware is the darkest with the least error. The fundamental reason bilinear fails at edges is that it's a low-pass filter. It assumes smooth color transitions at a discontinuity like the edge of the life preserver. It averages pixels from both sides of the boundary, red and white, get blended into something that shouldn't really exist. To put bilinear in context, let me briefly cover the spectrum of Demosaicing algorithms. At the simplest end is the nearest neighbor. Just copy the closest pixel at each color. We saw it scored 24.6 dB in our demo, clearly the worst. It's useful as a baseline. Edge-directed methods are the next step. They detect where the edges are in the image and then interpolate along the edge instead of across it. This directly solves bilinear's main weakness, the zipper artifacts at the boundaries. And gradient methods like Malvar-Cutler from 2004 start with bilinear as a base and then add a correction term using gradient information from the channel that is known. This exploits the fact that the R, G, and B channels in the natural images are highly correlated. And at the top end, deep learning approaches train a CNN to learn the entire demosaicing process from data. These achieve state-of-the-art quality and are increasingly what modern smartphone cameras use internally. But fundamentally, every one of these methods faced the same challenge. Two-thirds of the color information was never captured by the sensor. The only question is how you intelligently reconstruct it. Thank you.